right, so in this section now, we're finally going to start adding some routing to our topology. Up until this point in time, we've done all of our layer 1 and our layer 2 stuff. As far as layer 3, we simply added IPv4 and IPv6 host addresses to everything. So right now, as it stands, devices can IPv4 or IPv6 ping or telnet their directly connected peers, but they have no way of reaching remote subnets. And that's what we need to give them the ability to do. So, the CCNA expects you to know how to work with static and default routes, and so now we're going to get our opportunity to actually work on that. All right, so let's go into our objectives here. On R2 and switch 3, using static routes only, ensure that R2 can IPv4, IPv6 ping the addresses on switch 2's SVI5 interface. And that those pings will only work if we also do objective number 2 as well, because switch 2 has to have a return path to reply to those pings. And this particular case on switch 2, we're just going to configure a static default route to give him reachability to all unknown subnets. Now, let me give you something here. I don't think I've actually provided this in the files section. If not, this might make your life a little bit easier. Let's see. Well, I'll tell you what. Why don't you take just a couple of minutes to work that out, work out what those static routes will look like. And just as a recap, if we go back to this, we know that in order for R2 to ping the SVI5 interface of switch 2, and that is what we're told to do right here. If I go back to this, we got to reach the switch 2's SVI5 interface. We know that in order to do that, R2 cannot send packets across Fast Ethernet 01, because that's currently a PPP over Ethernet connection. And there's no way he can send regular Ethernet frames and PPP over Ethernet frames across the same interface. It's one over the other. So right now, R2 can use that to send packets directly to R4, but not to switch 2. So think about that when creating your static routes for R2 to reach SVI5's IPv4 and IPv6 address. So take a couple of moments now to work out what those static routes will look like on all the devices that need them. Okay, let's go ahead and work on that a little bit. I just created this, which is the same topology we've seen before, but this also has all of the IPv4 and IPv6 subnets in it, the ones that I derive. So if you're watching this recording and you're trying to rebuild this lab on your own, these subnets might not match what you have. But if you're following along with me in the live class, this PDF might be useful to you. So I'm going to go ahead and put this into the files section. All right, so it's in there right now. So just like before, go ahead and just refresh your browser, reload it, and then go to the Files tab, and you should see the IP subnets topology.pdf, which will help you follow along a little bit better when it comes to the subnets we're trying to reach. Okay, so here's what we need to do in order to get this to work. Let's just start with IPv4, because IPv6 will be almost exactly the same. So in router 2, if we want him to reach the IPv4 subnet on SVI5, or I would say, first of all, we're going to create a static route to the host address on SVI5. We could create a static route to this subnet. We could do that. But in reality, that's not really useful, because this particular subnet only has 3 hosts in it: router 4, router 2, and switch 2. And router 2 already knows how to get to himself. He already knows how to get to the host address of router 4. So the only address he doesn't know how to get to is the IP address on SVI5 for subnet F. So, and we were told to give him reachability just to that SVI so he can ping it. So I'm going to go ahead and create a host route in that router. Now, furthermore, we could do one of two things here. we could create just a single host route. And if we did that, we'd have to ask ourselves, what should be the next hop of that route? And we have a choice. We could take this path here and have the next hop be the IP address on SVI2. But if we do that and for some reason SVI2 goes down, now we've lost our reachability to SVI5. So to be on the safe side, we should probably create a second route going across here with the next hop of SVI3's address. So we're going to have two static routes in router 2. Both of them are going to be host routes. They're going to be giving him reachability just to the IP address on SVI5. One of those routes is going to have a next hop of SVI2. The other one is going to have a next hop of SVI3. So let's go ahead and work through that first of all. And I'll go ahead and do that in Notepad here. Okay, so let's get rid of all this stuff. Okay, so in R2, and move this over a little bit more so you can see it a little bit better. Okay, so in R2, I'll just simply go IP route 190.190.9.26. So with that mask, that's giving them a route to a specific host address. And the next hop is 190.199.42. So he can use that to get across VLAN 2. And then I'll give him another route that looks exactly the same with one small change. That'll be going to 9.46. And he can use that to go across VLAN 3. So all I got to do in router 2's routing table. So now in switch 3, I also have to give switch 3 reachability because switch 3 is not directly connected to subnet F. So same thing. I'm going to go ahead and switch 3 only needs a single route. Now you might notice in this PDF I sent you there's a subnet X. Actually, it shouldn't be X. It should be something else. Don't worry about that. We haven't created that yet. That will be created later on. So here, for switch 3, going to be the same route except he's going to be going to 9.54. That is switch 2's IP address in VLAN 1. And then lastly, so those will get the packets to switch 2. Now switch 2 needs to be able to reply to them. And the instructions told us to use a static default route in switch 2. So that will be IP route 0000, and then the next hop will be going right back to switch 3 again, which is 9.53. So these two routes here will get IPv4 packets to SVI5 on switch 2. And this route here will ensure that the replies get back to us. Now configuring the IPv6 route is pretty much exactly the same. IPv6 route 2222.110.0.bb06:22/128 because it's a host route. And this will be going to this next hop, which will be 0333. That's switch 3. And repeat it so we can send those packets across VLAN 2. Okay, on switch 3, repeat it, but we send those packets across VLAN 1. And this here, IPv6 route, that's how you do a default route. And the next hop is switch 3. Okay, so before I type those into my routers and switches, do you have any questions on what I've created right here or how they will work? Yeah, so someone's asking if I could go over the format of the default route. So in IPv6. So in IPv4, the default route basically says, look, all networks is denoted by all zeros, and then the network mask of all zeros means we're not really matching on anything. So the equivalent of that in IPv6 would be 128 bits of zeros. And certainly I could have typed that out longhand, which would be 0000, 0000, and then just keep doing that for 8 more octets. 1, 2, 3. So that would be, I could have done that. So this is equivalent to this. I may have done too many. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I did 2 of them too many. So this is just a shortcut. Because remember, we can condense all of our zeros down to just a pair of double colons. Are there any other questions? Okay, then let's copy and paste all this stuff in there and test out that we have connectivity. So let's start with R2. Okay. And then let's go to switch 3. Okay. And lastly, let's go to switch 2. And that should work. So now if I go back to router 2, I should be able to ping 190.199.26. That is the host address on SVI 5 of switch 2. Ah, good troubleshooting opportunity here. We'll have to figure out what's going on. Does my IPv6 ping work? Okay, my IPv6 ping is working, but my IPv4 ping is not. Okay, so some questions for you. First thing I would want to do is look in my IPv4 routing table of R2 to see if that static route is in there and if I did it correctly. So we've already looked at the routing table a couple times. Just quick review. What is the command to look at the routing table of R2, the IPv4 routing table? That's right. Thank you guys. That's show IP route. And when I go in there, what letter am I going to be looking for to indicate a static route? That's right. I'm going to be looking for an S. S for static. So actually I can just do show IP route static. I don't need to see all the other stuff. 190, 190, 9.26/32, okay, via 190.199.46 and 42. Okay, that looks good. Can I ping my next hops? That would be my next thing. Can I even reach the next hop? I can reach that next hop. And I can reach that next hop. Okay, so I can reach the next hop. So now we move on to the next hop and see what he's seeing. So switch 3 in this case. Show IP route static. Ah, what's this telling me? I mean, after all, I created the static route. You saw it. Let's go ahead and scroll up here, just to prove that I'm not crazy. Right here. Here was switch 3. It took the static routes. I never got any kind of error message. So why am I not seeing those, at least the IPv4? Why am I not seeing the IPv4 static route in here? Well, we're not doing kind of dynamic routing here, so there's no advertisement of any kind. The problem here is that multi-layer switches, most of them I'm aware of, even when you configure IP addresses, don't have routing enabled. IP version 4 routing is not enabled by default on multi-layer switches, which is kind of interesting that it even let me type in the static route to begin with. You would think it would bark out a complaint about that. But it took it, just didn't do anything with it. So I need to enable IP routing. And now when I look at my routing table, there it is. So that very well could have explained why and notice I had already done IPv6. Remember back when I configured my IPv6 addresses, I had already turned on IPv6 unicast-routing. And that's why my IPv6 ping was working, but my IPv4 ping was not. So now at this point, I should be able to, from router 2, ping that address of .26. Oh, if only it were that easy. Okay, we're not done yet. Still got a little more troubleshooting to do. Okay. So on switch 3, show IP route static, we have a single static route that says to get here, go to 9.54, which is the host address on switch 2's interface VLAN 1. Can we ping that? Okay, now we can ping it. Curious that he had to ARP for it first. He should have already ARP for it when he received the previous ping from router 2. 9.26. Let's try that ping again from router 2 now that the ARP has been successful in switch 3. Nope, still not working. Okay, next thing. Now let's go to switch 3 again. Can switch 3 ping our ultimate destination? Yes, he can. So, what have we learned? We've learned, if I go back to my topology diagram here, router 2 has the correct static routes directing its traffic to switch 3. Switch 3 has a static route further directing that traffic to switch 2. And we verified that switch 3 actually can ping this address right here. Router 2 cannot ping it. What do you think is going on here? Or what do you think is the next thing we should try to troubleshoot? Well, the next thing I might be wondering about is, what proof do I have, or actually I would be wondering, when router 2 does his ping, initiates those ICMP packets, are they making it all the way to switch 2, or are they not making it there? Maybe they're making it to switch 2, but for some reason, switch 2 is unable to reply to them. Oh, hold on a second. Didn't we have to just enable routing on switch 3? Maybe we have to enable routing on switch 2 as well so that switch 2 can reply back. Let's check that out. Show IP route. Yep, looks to me like routing is not enabled on this guy. Maybe that's our problem. Or I should say maybe that's our only problem. We'll find out. Show IP route. All right, that's better. Now he knows about his directly connected networks, and he has this here as a default. All right, maybe that'll work. Let's find out. There we go. Now our IPv4 ping works. That's really all we have for this section on default routes and static routes. They're a pretty simple concept in theory. So in the previous section, we enabled routing with static routes. And if we go back to the diagram right here, right now what we've done with static routes is we have given R2 the ability to send packets out either one of these sub interfaces right here, with the ultimate destination being SVI 5 on switch 2. And switch 2 can reply back to that. But no other remote subnets are currently reachable. Switch 2 would not, for example, be able to get to subnet A or B. Because even though switch 2 has a default route, and his default route saying, okay, anything I don't know about, send it to switch 3. Fine, but switch 3, all he knows about currently are his directly connected subnets and SVI 5. Switch 3 has no way of getting to A or B or H or I or any of these other ones. So rather than just enabling static routes on everything all over the board, which would be very tedious and time consuming, we're now going to go into enabling our first routing protocol of EIGRP to get full IPv4 and IPv6 connectivity throughout our topology. All right, step 1, remove all static and default routes from router 2, switch 2, and switch 3. So let's get rid of that stuff we just did. So I'm going to do show run section IP route. And now I can just copy and paste these and get rid of them. Do show run section IPv6 route. Yes, unfortunately switches don't support the section command. Begin IP route. And the last one to get rid of is switch 2. Okay, so we've just accomplished task number 1. On all devices except switch 1, save your current running config to flash memory, renaming it pre-EIGRP. So type in the live question feed for me. What is the actual command I would issue to accomplish task number 2? That's right. Thank you, Jonathan and Abu Bakr. That's right. It's the copy run flash command. So let's just start with the start on my menu here. I'm going to skip switch 1, so we'll start with switch 2. Copy run flash colon pre-EIGRP. Now, if you're watching this as a recording, and if you're actually doing this on I&E's equipment using rack rentals and stuff, there is a possibility that someone may have used the rack before you and done this exact same lab, and that pre-EIGRP might already exist in the flash memory. If it does, you'll see something like this. You'll say, do you want to overwrite? Just say yes, because you don't know if the previous learners pre-EIGRP used the same addressing scheme as you. There might be some other differences as well. So just overwrite theirs with yours, so there's no conflict. Okay, it looks like we got some duplicate steps right here, 3 and 4. Whoops, that's a mistake. Okay, let's go ahead and fix that. Where's my editor? Fire that person. Okay, so let's get this right here. Oh, that's me. Okay. All right, so my my numbering is going to be a little off here, but bear with me. I just don't want to waste your time fixing that. So let's assume we did steps 3 and 4, and now we're on step 5. Configure all devices in this lab, except for switch 1, for EIGRP, IPv4 and IPv6, adhering to the following guidelines. Then we've got guidelines out the ear. So let's see what our guidelines are here. Router IDs of all devices should take a particular format. And we're told right here what that format should be. So our router IDs are predictable and visible, clearly visible in the output of commands. Specific IPv4 network statements should be used, including wildcard masks, to ensure that all layer 3 interfaces are active for EIGRP. Now, the reason why that particular thing is in here is because with EIGRP, you could always type something like this. And that right there would include all of your interfaces in EIGRP. But that's too easy. That's too simple. We want to make it a little bit harder for you, so we're going to have specific network statements for every single one of your interfaces, along with the appropriate wildcard mask, just to make sure you really get it. C, prevent EIGRP hellos from being generated on loopback interfaces. Curious. How would we do that? Go ahead and type in the live question feed. How would we accomplish step 5C in our devices that do have loopbacks? That's right, Abu Bakr, that's correct. We would use the passive interface command, and we'd have to use it multiple times, like passive interface loopback 0, passive interface loopback 1, and so on and so forth. EIGRP security should be implemented on all devices using a password of INE. Oh, that's going to be fun. When completed, router 2 should be able to v4 and v6 ping any of the IP addresses on router 3's and router 1's loopback interfaces. So far corners of the topology. And then we'll do 5F at the end. But for now, we're just going to do 5A through E. Okay, so let's bring up Notepad here. Get rid of all this stuff. Okay, so let's say that we were to start with switch 2. Okay. Okay, so on my first device where I'm configuring EIGRP, let's say I'm at this prompt right here. What would I type to enable my EIGRP process? Yeah, so right here I'd have to type router EIGRP, and then after that I'd have to select some sort of autonomous system number. Now this particular lab has not told us what autonomous system number to use, so we can pretty much pick anything as long as it's consistent across all of my devices, because they all have to match. So I always like doing, I don't know, for some reason I like EIGRP 100, I have no idea, but I just like that. So router EIGRP 100, and that'll put us into config-router mode. Okay. Now it says here that it should take on a specific router ID. Now if I'm on switch 2, it should be 22.22.22.22. How can I ensure that switch 2 uses that EIGRP router ID? What command can I type? And would I type it right here? So remember, right now I'm at config-router. That's my prompt. What command would I type? And where would I type it? Thank you, Abu Bakr. You're very close. I think you're missing one keyword. It would be the EIGRP router-ID command. In some routing protocols, you just have to type router-ID, but EIGRP is kind of a stickler and actually requires you to type EIGRP router-ID. So EIGRP router-ID 22.22.22.22. Okay. And then we want some specific network statements for IPv4. Okay, so look at your topology diagram I just sent you. And I'm just going to go ahead and type them in here so you can follow along. So we're looking at switch 2. So I would say network 190, 199. So they're all going to start with that. And he's got .24. And because he got a /29, that would be 000.7 would be the wildcard mask for that. And then he's also connected to 9.52. And because that's a /30, that would be 000.3. And that's it for switch 2. Those are the only 2 networks that he's connected to at the moment. Prevent EIGRP hellos from being generated on loopback interfaces. Well, switch 2, he doesn't have any loopbacks, so we don't have to worry about that. EIGRP security should be implemented on all devices using a password of INE. Is that something that I would do right here, where I'm currently under config-router mode? Or is that something where I would do elsewhere? And if elsewhere, where would I do it? Yes, thank you guys. So everybody's replying back under the interface. That's right. Actually, in order to do authentication for EIGRP, it's a multi-step process. And some of the commands are done under the interface, some of the commands are done at the global configuration level. Okay? So you actually enable the authentication under the interface, but where you put all of your passwords is at the global configuration level. So I will go ahead and exit out of here. And so for switch 2, I'll say, so to begin with, I would configure my authentication credentials, and you do that within something called a keychain. Now I always forget if there's a dash in there or not, so let's just go ahead and test it out real quick. Okay, so there's no dash, just keychain and then the name. So we'll say INE. And then you would have key ID, Also no dash. Oh no, it's just key, the number. The number of your key. And this is where you have key dash string, and this is where you actually have your password. And I believe we were told to use a key string of what? Capital INE. Okay, now I go into my interfaces. And in my switch, that would be interface VLAN 5. And I do IP authentication EIGRP. I have a hard time remembering these ones as well. Key dash string. Let's just go ahead and go into switch 2. Yeah, it's come on, what is it? Mode. And then it's EIGRP 100, and then you say MD5. And then IP authentication key dash string INE. Nope, IP authentication key dash chain. And that's also EIGRP 100. I believe that's the syntax there. Let's just check that out. Yeah, key dash chain EIGRP 100 INE. Great, and then I just also do that in interface VLAN 1. And that will complete my configuration for switch 2. Right, so I've got the 190, 190, so that's a class B. So I have a request to talk a little bit more about the whole, keychain and authentication mode and all that stuff. So when we get to OSPF, OSPF, when you're doing authentication, it actually provides you a choice. You could configure all of your OSPF authentication, including your password called a key, right under the interface, right there with like a couple of commands. Or you could refer back to a keychain like I'm doing here. EIGRP doesn't give you that choice. So with EIGRP, your keychain, you give it a descriptive name, like in this case INE, and then you put one or more keys in there, which is another way of saying password. Now in this particular case, my keychain only has a single password. So key 1 is sort of like saying password number 1, and my first password is INE. Where the real power of a keychain comes into play is where you have multiple passwords, like key 2, key 3, key 4, and you have different key strings for each one of them. And then within a keychain, you can even have it related back to time. You could say, okay, from 12 o'clock until 4 o'clock on December 4th, I want to use this password. And then from 4 o'clock until 7 p.m. for the next 18 days, I want to use key string number 2, and then key string number 3. That's the real power behind using a keychain, is you can have multiple passwords, multiple key strings, and you can have them time-based. Did not build that into this lab because there was no way for me to really accurately make sure that anybody doing this lab, whether it be tomorrow or a year from now, set the appropriate time and had everything synchronized up. We will be using NTP later on, and I probably could have put, no, it wouldn't have worked because all the devices would have to be synced up with NTP first, and that would require that routing is there, because if my NTP server is several routers away from this guy right here, if there's no routing, they can't talk to each other. They can't communicate. So it's sort of the, the chicken before the egg thing. So in this particular case, we're just using a simple key chain with just one key string. And then under the interface, we say, okay, I want you to do MD5 authentication, which means I'm going to do a hash of this key so it's not actually sent in clear text. And that's the only kind you have in EIGRP. With OSPF, you've got plain text authentication or MD5 as a choice. EIGRP, you don't have the choice. So this here is saying, okay, I'm going to do authentication in Autonomous System 100. I'm going to do MD5. And the next line says, here's where I'm going to pull my password from. I'm going to pull it from the keychain called INE. So that's how all of that sort of works together. All right, so now that we've got that, we should be able to copy and paste most of this into some of our other devices. Let's just go to switch 3 here. I'll change some of these, but let's just start out by copying it. Okay, so switch 3. Let's see here. His router ID will clearly be different. And his networks, he does share the 52 network, but he doesn't have 24, so he's got the 40 network, which is a .3. He also has the 44 network, which is a .3 wildcard mask, and he has the 48 network, which is also a /30. Everything he's connected to right now is a /30. So switch 3 is connected to 4 subnets. We got them all in here, right here. No loopback, so we don't have to worry about that. Got the keychain and my interface VLAN. So we'll just say we're going to put on interface VLAN 1, interface VLAN 2, interface VLAN 3, interface VLAN 4, and that's it. He's got 4 SVIs. So that should cover us for switch 2. Let's just go ahead and copy and paste that in there right now, just on these 2 devices. There's switch 2. And now let's do switch 3. And we should see switch 2 and switch 3 become neighbors, and there we are. Right there. That shows that switch 2 and switch 3 just became neighbors across VLAN 1. Okay, let's go ahead and now do router 2. Let's just do them numerically, actually. Router 1. So router 1, we can copy a lot of the same stuff. So his router ID will be 1.1.1.1. And we're going to have to modify some of these statements here. So we're going to have the 56 network. That's his connection to router 4. And we're going to have the 32 network. That's network H. Now that has a different mask though. That's going to be a .7. And the 60 network, That's his point-to-point connection to router 3. Okay, and now we got to include his 3 loopbacks. So the first loopback is 8.224, and that is a /27. So that'll be a .31. And we also have 9.16, which is loopback 1. And that's a /29, so that will also be a .7. And then lastly, we have network 3.3.3.0. Okay, now we do have to make his loopbacks passive. Passive dash interface loopback 0. Loopback 1, loopback 2. Okay, that should do that. Now the keychain, we're going to implement that on interface serial 1/3. And before that, we're going to implement it on serial 1/0.134. And 1/0.132. So that will be our configuration for router 1. Let me know if you have any questions about what you see right there. Okay, I'm going to start saving these configs because we're adding a lot of stuff to these. It'd be a real shame to lose this stuff. Okay, so that was router 1. Now let's go to router 2. Router 2 will be very similar to this. He will be in router ID of 2222. He doesn't have as many networks that we have. Well, actually, he does. So we've got 8.0. That's his loopback 0, and that is a /25. So that'll be a .127 subnet mask. His loopback 1 is 9.0. That's a /28. So that'll be .15. His fast Ethernet 0.1 is the .24 network. And that is a 29, so that subnet mask is okay. And then his subinterface 00.1 is .40. And his subinterface 00.3 is the 44 network. All right, that should cover all of the networks on router 2. Let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, I think I've got all of them here. And then the only thing I have to do is interface fast Ethernet 0.0.2 and interface fast Ethernet 0.0.3. Fast Ethernet 0.1. Okay, any questions on what I've created here for router 2? Almost done. And adding IPv6 to this is going to be a piece of cake. Because our, well, you'll see. So router 2. Great. Great. So currently he formed a neighbor relationship with switch 3 across both of his sub-interfaces. I haven't configured router 4 yet, and he can't form, even though he shares subnet F with switch 2, we're still doing PPP over Ethernet, and so there's that still layer 2 mismatch between router 2 and switch 2. So at present, router 2 and switch 2 cannot form a neighbor relationship. Okay, now let's go into router 3. Router 3 is going to be very similar to router 1. Okay, so this will be 3333. And let's take a look at his networks. So he's got the .34. Let's start with his loopback 0. That is 8.128, and that is a /26. So that'll be a 63 mask. And then he's got 8.192. And that is the /27 subnet mask. And 3331, let's just put this up here so we keep them consistent. Actually, it's a 331. Oh, I think I mistyped the network statement on router 1. I'll have to go back to that. So this is 3330. Router 1 should have been 3310. There we go. Okay, so so that covers my first 3 loopbacks right there. Now let's take a look at my physical interfaces. I need the .32 network, and I've got that. Okay, I need the .60 network. These other 2 don't need to be here. So I've got 2 physical networks and 3 loopbacks. All right, that should do it. And let's see here, it's serial 0/0/0.134 and 0/0/0.132. Okay, great. We have an EIGRP relationship up across our point-to-point sub-interface. Now, why do we not have an EIGRP neighbor relationship across subnet H? Well, we'll come back. We'll come back and we'll troubleshoot that. Last guy to figure out is router 4. Okay, router 4. Okay, so he's going to be 4444. He's connected to the 32 network and the 56 network. Let's get rid of these. The 56 network is that looks good. 32 network, that looks good. Okay, now we also have to include the 2 Ethernet segments. network 190.190.9.48. That's the connection to switch 3. 190.190.9.24. That's the connection to router 2, the PPP over Ethernet connection. Okay, he doesn't have any loopbacks right now, so we don't have to worry about that. Okay, he is serial 1/0. He is also fast Ethernet 00 and 0/1. Hold on just a second here. Now he's currently doing PPP over Ethernet, so his fast Ethernet 01 doesn't have any layer 3, so I actually need to convert this to his virtual-template 1. That's the interface that would be doing layer 3 EIGRP. Okay, I think that completes it here. Let's go ahead and put this into router 4. Okay, so we've completed our IPv4 EIGRP. Before we move on to the IPv6 EIGRP, we want to validate all this, make sure it's working okay. So what would you do? Let's just start where we are right now with router 4. What would you do to verify that EIGRP is working as expected on router 4? Probably more than one approach to this question, so I just want to see what you guys come up with. Yeah, Abu Bakr, I would agree with you. I would start by displaying my EIGRP neighbors. If I go back to my diagram right here, router 4 should have one neighbor. He should have switch 3, router 2, router 3, and then you should have 2 connections to router 1. One connection over the frame relay, one connection over the PPP. So I should see a total of 5 neighbor relationships. Oh, and, well, let's see here. He won't be able to talk to switch 2 because he's doing PPP over Ethernet still. So I should see 5 neighbor relationships. So let's take a look. Show IP EIGRP neighbor. Uh-oh. Okay, I don't. So let's see here. We've got our neighbor relationships across serial 1/0, so across the frame relay cloud. Don't have a neighbor relationship via PPP to router 1. Because I didn't include it on serial 1/3. That's why. I don't have authentication going, and so that will fail. Yep. So let's put that in there. Okay, so we should see that neighbor relationship. There we go. But we're still missing our neighbor relationship across the PPP over Ethernet connection, fast Ethernet 0/1. Okay, so let's check and see if everything's looking good there. So show IP interface brief. First one I want to check is 01 up. Yes, it is. Okay, my virtual access, where's my virtual template? Virtual template being down, that's not a big deal. When the PPP over Ethernet session comes up, it creates out of thin air this virtual access interface. So the fact that we see the virtual access interface up, that's good. Now let's see here. Can I ping my neighbor? All right, something's going on because I cannot ping router 2. Okay, so we need to troubleshoot this. I don't believe I changed any of the configuration in router 2. Didn't think so. Show run. Oh, wait a second. I think in router 2 I forgot to include my Ethernet over my dialer interface. Yeah, see, I did it here under the physical interface. That's wrong. It should have been done under the dialer interface. There we go. Okay, so, well, while we're here, let's just go ahead and work our way from left to right. So router 2, show IP EIGRP neighbor. So he should have a total of 1, 2, 3 neighbors, and he does. That looks good. Let's take a look at switch 3. Show IP EIGRP neighbor. He should have a total of 1, 2, 3, 4 neighbors, and he does. Okay, great. Let's go to switch 2. Switch 2 should only have a single neighbor. That's right, he does on VLAN 1. Okay, we already verified router 4, but we'll just take a look again. And yep, he's got a total of 5 neighbors. That's what we expect to see. So lastly, let's just jump over here to router 3, and he should have a total of 3 neighbors. Yes, so he's got a neighbor across the point-to-point connection, and then across the frame relay, he's got a neighbor relationship with router 4 and router 1. Okay, so this is what I'm going to do next. Now it says here, what I'm going to do is I'm going to go back to router 2, and I'm going to do this command. Actually, let me do a question. Question for you guys. I want to issue a command on router 2 that'll give me a count of how many routes he knows about. I don't really care to see all the different subnets and masks and next hops. I just want to see a total count of how many subnets he knows about, how many EIGRP routes he knows about, because I know I've got everything working right now. And I want to take a screenshot of that output so that in the future I can refer back to that screenshot to see if I'm missing something. So what is the command I would type in to see that kind of routing information? Just a high-level overview of how many routes I have. The command I'm looking for is show IP route summary. And so here we see when I've got a fully functional IPv4 network where everything knows about everything, I've got a total of 2 classful networks, right? So I've got the 190/190, so that's a class B, 190/190, and I've got the 3 network. And then everything is a subnet of that. So I've got 2 classful networks and a total of 23 subnets that I've learned about. So I'm going to take a screenshot of that. So if at any point in time a ping's not working or something, I can refer back to this and see if I'm missing a route. Okay, great. Now while I'm here, let's just do an end-to-end ping. Let me ping 3331. That is subnet X on router 3, otherwise known as loopback 2. And that's it. So I got all the way across. Fantastic. With IPv6, main thing I have to do is go to my interface, because you enable IPv6 routing protocols at the interface level, not within a global process. There's no such thing as a network command for IPv6. So here I would just say IPv6 EIGRP 100. And that's all I got to do. I'm just going to copy and paste that across all of my interfaces. Okay. Almost done. See, it's so much easier without having to deal with all those network statements. Okay, so that's part of it. Now, when I do that, that will create a global IPv6 routing process, and if I just left it alone, those processes would come up with, they would not come up with the router IDs that I want them to come up with. So I now have to go IPv6 router EIGRP 100. Let's just see what the exact format of this is. Okay, I think this is still the EIGRP router-ID. Yep, okay. Actually, I can just do this. Okay, now there may be one additional command that we have to type in here. I know that when IPv6 EIGRP first came out, that even when you created a global process for it, that process was shut down by default. And you actually had to do a no shutdown within the EIGRP IPv6 router process to get it to work. It may be that with more recent code, it's now on by default and you don't have to do that. So I'm going to leave out the no shutdown command right now and just see if I can get this to work just the way it is. So let's start once again with switch 2. The other thing about this is, let's go into one of my layer 3 interfaces. You know, with when we were dealing with authentication with EIGRP version 4, it was IP authentication mode EIGRP, and then 100. But notice this is IP. So you might think, okay, well there must be an IPv6 equivalent, right? IPv6, well, looks like it. Authentication mode, oh, looks like there is. Where I'm a little surprised by this is that with some of the other routing protocols, with, for example, OSPF, with OSPF, in order to get it to do IPv6 authentication, you have to use IPsec. And the CCNA does not expect you to know how to configure IPsec. But it looks like with EIGRP, we don't have to do that. They retain the old format of authentication. So, that being the case, a little bit more copying and pasting to do here. Okay, so let's go ahead and get this in here. Almost done. That should do it. Okay, wow, I probably should save this thing before my computer crashes and makes me cry. All right, let's just paste all this stuff, but a lot of it's redundant, but let's just paste it all back into switch 2 again. There we go, save him. Let's go to switch 3. Great. Let's go to router 1. Okay, let's go to router 2. Router 2, I did not include my loopbacks. Need to include those. Interface loopback 0. I just have to have the IPv6 command under that. need to go back and do that on router 1 as well. Here, while I'm thinking about it, let me go ahead and put this in router 1's configuration. I should be doing the passive interface command as well within my EIGRP v6 process, but I'm not going to. You guys can do that. I'm not going to do that. So router 2. There we go. Notice something that I want to call your attention to while I'm here. Notice that when my EIGRP IPv6 adjacency is coming up, notice that I'm forming a neighbor relationship with my neighbor's link local address, FE80, not my neighbor's global address. That's going to be important when I do EIGRP across that frame relay cloud, giving you a little hint there about something we might have to do to get that working. That's router 1, that's router 2, so now let's go to router 3. Now router 3 also need to enable it on the loopbacks. Okay. And lastly, router 4. Okay. Oops. Okay, so let's get rid of this for now. All right, so let's see. Once again, do our verification here. Router 2, same thing. On router 2, I should have a total of 1, 2, 3 IPv6 adjacencies. And I do. I've got those 3 neighbor relationships. Just copy this command here. All right, let's now go to switch 2. He should only have a single neighbor relationship. He does. Let's go to switch 3. He should have 1, 2, 3, 4. Yep, he's got 4. Now, continuing moving left to right, let's go to router 4. So initially, this might look okay, right? I mean, after all, if we look at the diagram, our topology diagram, it looks like router 4 should have, let's count them up, an EIGRP v6 relationship with router 2, switch 3, across the PPP connection to router 1, across the frame relay connection to router 1, and across the frame relay connection to router 3. We should have a total of 5 relationships, and it looks like we do. But there's one little indicator in here that something isn't quite right. Can anybody spot what that is? This might be a little tough because this is really sort of now getting into the CCNP realm, because at the CCNA level, they expect you to look under the address field and look for the addresses of the neighbors you're expecting to see. They expect you to look under the interface to verify that the neighbor has been learned under the correct interface. Yeah, Abu Bakr, you got it. The Q count column. Ideally, we want our Q count to be 0. When it's a non-zero number like this, that means that I have attempted to send an EIGRP reliable packet to my neighbor, and I have not gotten an acknowledgement back. Remember, with EIGRP, we have the concept of reliable and unreliable packets. For example, an EIGRP hello is called an unreliable packet. When I send you an EIGRP hello, I don't expect you to send me an acknowledgement back for that. But if, for example, I send you an EIGRP update or an EIGRP query or an EIGRP reply, you need to acknowledge that back to me. And if you don't, I mark my Q count as 1 and I try to resend it to you. And that Q count keeps going up as I keep trying to resend to you. Now remember, how does EIGRP form a neighbor relationship? It forms a neighbor relationship by saying, okay, I'm going to transmit a hello, and then when I see your hello, I'm going to transmit an EIGRP update. And then when you send me acknowledgement back, great, now we can be friends. So this is showing us here that something isn't working, and clearly, look at this, retry limit exceeded. So our EIGRP neighbor relationships across the frame relay multi-point interfaces are not working. What do you think we need to do to fix this? And this is just an IPv6 problem. IPv4 was just fine. Remember, show IP EIGRP neighbor. Q counts are all 0 for IPv4. But for IPv6, I'm having some problems. So it's been recommended to change the network type. I don't think you can do that for EIGRP. That would be a potential solution for OSPF, but I don't think EIGRP even has the concept of network types. So what else could I do here? Well, here's our problem. Let's take a look. Show run interface serial 1/0. Notice that when it comes to IPv6, I've got some frame relay maps for my neighbors. But here's what's the problem. These frame relay maps are for the global addresses of my neighbors. But EIGRP does not use global addresses to form a neighbor relationship. It uses link local addresses. That's my problem. I need to add some more frame relay map statements to map my neighbor's link local address to the appropriate DELSI I use to reach that link local. Okay, welcome back. This video we're going to continue on with where we left off with EIGRP. So just to give you a quick refresher on where we left off in the last video, let me go ahead and bring up the topology diagrams again so we can look at that. So let's take a look at the layer 3 diagram. So where we left off was that we had all of our IPv4 and all of our IPv6 addresses are already done here. At the moment, network I is a PPP connection, so we have PPP running across that serial 1/3 between router 1 and router 4. And between router 2 and router 4, that is a PPP over Ethernet connection. We're doing PPP OE. And because of that, even though switch 2 has an IP address in the same subnet as router 2 and router 4, switch 2 cannot use that subnet to talk to them. because switch 2 doesn't do PPP over Ethernet, it just does straight Ethernet. And an interface can do one or the other. So, so that's where we are, and also we left off where we had configured basic EIGRP on every single subnet in this topology, both our IPv4 and our IPv6 subnets as well. And we also configured EIGRP authentication, so that's done. Now, where we left off was EIGRP was pretty much working except across frame relay. It specifically network H. It was working on network J, that's a point-to-point frame relay connection, and there was no problems there. We had our neighbor relationship come up just fine with router 1 and router 3. But on network H, which is our multi-point frame relay, we were not able to get it working. And at the very end of the last video, I talked about how the reason for that is that when you're doing IPv6, actually it was working for IPv4. EIGRP was working for IPv4, but it was not working for IPv6. And the reason for that is with EIGRP for v6, two routers form a neighbor relationship using each other's link local addresses. Remember that with IPv6, you've got the concept of the moment you enable it on an interface, even before you configure any IPv6 global address, every single interface, even interfaces on your laptop and your PC, dynamically and automatically create something called a link local address. And it always starts out with FE80. You'll definitely be expected to remember that FE80 is what you should lock onto, that is the format of a link local address. Specifically only used to talk to people on the same local link as you, or another way of saying that is on the same broadcast domain as you. So that's how routers form their EIGRP neighbor relationships in the world of v6, is by using link local, which is actually kind of nice because that means, I mean, if we think about it, let's think about how IPv4 works. If I have two routers connected to the same broadcast domain, it's assumed that their IPv4 addresses will be in the same subnet. As a matter of fact, if they're not in the same subnet, EIGRP will not work. They will not form a neighbor relationship with each other. You'll actually get every 5 seconds or so an annoying error message saying neighbor not on common subnet, and you'll see that over and over and over again. Well, with v6, that's not an issue. With v6, not sure why you'd want to do this, but you could do this. You could have two routers on the same broadcast domain, but router A could be in a completely different global network like the 2222 network, and router B could be in the 22AA network, totally different IPv6 networks, but because they share the same broadcast domain, they could still form an EIGRP v6 neighbor relationship because they're not using those addresses to talk to each other. They're using their link local addresses that start out with FE80 to talk to each other. So why do we have a problem with that here? Well, when we were configuring our frame relay, back when we were trying to get just regular IPv4 and IPv6 to work across network H, on our multi-point interfaces, so that's serial 1/0 on router 4 and the .341 and .141 on router 1 and 3. On those multi-point interfaces, we had to create frame relay maps. What we didn't do, because we didn't really think about it at the time, was we didn't create any frame relay maps to reach my neighbor's link local address. The only frame relay maps we have right now are frame relay maps so I can ping my neighbor's global address. So that's what we need to implement at this point. We need to create some frame relay maps on all three of those routers, giving them the DELC number mapped to the link local address of the neighbor. And then EIGRP will be able to complete itself for IPv6 across that cloud. So our next step is we have to log in to each one of those routers and find out what their link local addresses are and create some frame relay maps to do that. And once we do that, sections 5A through 5E will be done. We'll be done with that. Okay, so let's go into our topology. And what I'm going to do is I'm going to bring up Notepad here, and just it'll be easier for me to keep track of the link local addresses and the DELCs used to reach them by doing this. So I'm going to say R4, R1, R3. Okay, so let's go ahead and figure out what the link local addresses are for each one of these. So let's start with R4. Okay, so let me ask you a question. We know that we're concerned with the link local address on R4's frame relay interface. How do I obtain that information? How do I figure out what his link local address is for that interface? What command would I type? Well, the command we'd be looking for is show IPv6 interface. So show IPv6 interface, and I'll just focus in on the one interface I'm really concerned about, which is serial 1/0. And there is my link local. So let's go ahead and copy that. All right, let's do the same thing for router 1. Oops, don't need to configure. Show IPv6 interface serial 1/0.134. That's all I really care about. There we go for that guy. And router 3. Yep. Show, so used to doing config T. Show IPv6 interface serial 000.134. All right, so now I've got all 3 of them. And what I'd like to do is just work out my configurations here in Notepad first, and then copy and paste it in. So for R4, we know we're going to have to do frame-relay map IPv6. And here I'm just going to put R1 link local. And then to reach R1, he's going to be using Delsi 141. Actually, probably the keyword broadcast won't even be relevant because broadcasts aren't relevant in the world of IPv6. And what I'll do is I'll replace that R1 link local with the actual link local address. I'm just making something that's nice and easy for me to copy at this point. And this will be R3 link local, and that will be 341. All right, and now let's do it for R1 and R3. So for R3, he's going to be for R1, he's going to be talking to R4 and R3. So from R1 to R4 is Delsi 141. We got that. From R1 to R3 is Delsi 131. Okay, and lastly, from R3 to R1 is 131. And from R3 to R4 is 341. Okay, great. So now all I got to do is just replace this stuff. So here we go. Here's R4's link local address. So anywhere I see R4 here, I'm just going to copy and paste that in. Okay, here's R1. So anywhere I see R1, I'm going to copy and paste that in. And R3. And that should do it. So let's go ahead and copy and paste these in here now, starting with R4. Well, since we're on R3, let's just do R3. I'm curious, I don't think these frame relay maps for IPv6 support the broadcast keyword, but I'm always open for surprise. Look at that, it actually still contains that. It's certainly not for broadcast because in the world of IPv6, there is no such thing as broadcast. But this broadcast keyword also allows multicast to go across, and we certainly need multicast because that's what EIGRP utilizes. All right, so let's just include the keyword here on these. There we go. Okay, so that was R3. We're done with him. Let's go into R1. And as soon as I copy and paste this into R1, we should see within just a matter of seconds R1 and R3 becoming EIGRP neighbors. Hopefully. Okay, let's see. Come on, let's see it. Oh, you know what? I think I turned off logging console. Logging console 6. I may have already missed it. Show IPv6 EIGRP neighbor. Still not quite working because remember we got this queue count here of 3 and we don't want to see that. Let's see if we can now ping the link local address of my neighbor. Ping. I want to do, well, let's make it easy. Ping to R3. That's this one right here. And that's going to be serial 1/0.134. Okay, fine. You want to be finicky. Okay, so I can ping the link local. That's good. So at this point, that should be all I need. It might just be taking a little bit of time. Let's check it again. Well, my queue count. No, wait a second. We're okay because I have 2 neighbors on that interface. This one with a queue count of 3 is router 4. And I haven't configured router 4 yet, so that's why I'm not able to reach him. This one here, that is router 3. And you can see that because up here when I pinged him, that ping ended with 6DD8, and here we have 6DD8. Queue count, just as a refresher, means, you know, with EIGRP, you have the concept of reliable and unreliable packets. Reliable packets are those EIGRP packets that require an acknowledgement, like an update or a query or a reply. And normally when you send out a reliable packet, within like a split second, you get an acknowledgement back. However, if you send out a reliable packet and a certain timer expires and you did not get your acknowledgement back, then you increment the queue count and you retry that packet. So this is an indication here that I've tried sending some EIGRP reliable packets and I'm not getting my acknowledgement back from my neighbor, so it's always an indication of some kind of a problem. Lots of things could cause that, but you don't want to see anything other than a 0 in that column. 0 is good. That means I'm getting acknowledgments for all of my reliable EIGRP stuff. Okay, good. So let's go ahead now and complete our configuration on router 4. Interface serial 1/0. Actually, let's turn on console logging. All right, let's finish him up. Router 4. And it shouldn't take too long. Show IPv6 EIGRP neighbor. Good, everything is 0. And I've got those 2 neighbors now across my serial. I haven't seen the EIGRP syslog yet, but that should be coming up any moment. But this is what I'm looking for. I'm seeing those 2 neighbors across that frame relay multi-point interface and that the queue count is 0. So we're good, everything's fine. So now let's go ahead and go back to the far corner of our topology, which is router 2, and see if we can ping the IPv6 address on, let's just choose router 3's loopback 0. So that would be ping 2222.1100.0 BB0B. By the way, if you don't have the IPv4, IPv6 topology diagram open in front of you that's got all the network numbers and where they are in the clouds, you might want to open that. It'll be easier to follow this way. And there we go. So I've got end-to-end connectivity. I can ping all the way across. Great. So that completes us from 5A through 5E. Do you have any questions before I move on to 5F? Okay. Oh, by the way, I probably should have mentioned this a couple of days ago, but clearly there is a little bit of network delay between myself and you guys. I've noticed that a lot of times when I ask if there's a question, it could take 20 or 30 seconds before I see your question come in. And it's probably because it takes a while for you to see me and hear me and then for you to get your question back to me. So do this for me from this point on. When you hear me say, what questions do you have, or do you have any questions? If you do have a question, just real fast type in why or yes and then hit enter. And once I see that, that'll be my cue that, okay, I need to sit back and relax and give this person another couple of seconds to type in the text of their question, okay? So let's just have that as our convention here. Okay, so 5F, modify EIGRP on any necessary devices such that the only IP route the router 2 should have to reach subnet X is 3000/8. So let's bring up our topology diagram again. Where was it? Right there. Ah, this one doesn't have network X. Where is that? Just one moment while I bring up the one that's got all the networks on it. This is the one we want to see. Okay, so right now, router 2 should know about the specific subnets of 333 and 331. Let's verify that, see if that's true. Show IP route. And because I want to see just my EIGRP routes, show IP route EIGRP. Yep, see, he's got the 2 specific subnets. And what that task is asking us to do is it's saying for this subnet right here, which is network X, we do not want to see it as 3330/24. We only want to see it as 3.0.0.0/8. So what do we need to do? What command do we need to implement? And where do we need to implement it in order to accomplish this objective? Harrison, you're very, very close. You just have one keyword in there that actually we want to take out. And Abu Bakr, actually you're correct, but your suggestion is a CCNP suggestion. At the CCNA level, people aren't expected to know that particular command. So what we're talking about here is summarization, right? So we want to get router 3, instead of sending the specific subnet, we want him to summarize that subnet down to its classful network, which is the 3 network /8. Now there's a couple of different ways to do route summarization, but at the CCNA level, the only way that you are taught to do it is using the auto summary command. When you get into CCNP route, if you guys actually pursue that, you'll see that there's another command called the IP summary-address command that you can do on the interface level, but we don't do that at the CCNA. That's the CCNP level. So what we need to do is we need to use auto-summary. And the way the auto-summary works is it should be implemented on the router that's directly connected to that subnet. If I tried implementing auto-summary, for example, on router 4 or one of these switches, it would not do what I want it to do because they are not directly connected to the 333 subnet. So it needs to be done on router 3. And then he will take that and automatically summarize it down to its classful boundary. Okay, so let's go ahead and do that. Let's go on to router 3. Oh, that's not the right guy. Router 3, come on. There you go. And what you'll notice is that in EIGRP, there's some changes that when you make the changes, it causes EIGRP to actually temporarily lose its neighbor relationships and then regain them again. And this is an example of one of them. Whenever you implement summarization, or you change summarization, or you turn it off, or if you do any kind of filtering, that causes EIGRP to bring down its neighbor relationship and then bring it back up again. So we'll see that the moment I change my summarization. Now, before I do anything here, if I want to see, without doing show run, without the show run command, if I want to see if this router was already running with the auto summary command or if it was not doing auto summary, what show command would I implement to verify that? Not show run. What other show command could I do? The command we're looking for is, yeah, show IP protocols. That's right. I have to preface it with do, since I'm at a different level here. Do show IP protocols. And we should see in here, for EIGRP, automatic summarization disabled. The default behavior really depends on the flavor of iOS that you're running. In, I believe, all of the 12-something versions of iOS, auto summarization is on by default. And then when they switched over to 15, I'm not sure if it was 15.0 or somewhere after that, but somewhere in the 15 train is when they decided to make auto summarization disabled the default. And actually, I think if we do a do show run section EIGRP, see, notice here under my router EIGRP, it doesn't even make mention of it. Doesn't even tell us if auto summarization is on or not. So we know it's off because it said disabled, so now I'm going to turn it on. Auto-summary. And now I'm going to lose my relationships. There they go. They're bouncing for a moment, only for a second. But if this is a production network, probably wouldn't want to do this in the middle of the afternoon. And now if I do show run section EIGRP, now we see auto summary in there because that is a non-default configuration. Okay, so let's go over to R2 and verify that it worked. Show IP route EIGRP. And there we go. We no longer have the 3330 network. Now we have the 3000/8 network. So that completed our objective for step 5F. Task 6, view the current IPv4 routing table on R1 and verify that there are 2 paths for every LAN reachable via R4, subnets A through G. Okay, so let's go ahead and take a look. We're on R1 we need to get to. Show IP route EIGRP. So let's do a quick look here. So let's see, subnet A is the 8.0/25. Is that in here? Yep, here's 8.0/25, and yep, we have 2 paths for it, serial 13 and 10. How about subnet B, 9.0/28? Yep, we got 2 paths for that. So it looks like right now, for the vast majority of our networks, we do have 2 equal cost paths. To reach them, we can either go out our PPP interface, or we can go out our frame relay interface. Okay, so we verified that. View the current table on R1 that is used to store EIGRP information to see if there are any other paths that R1 knows about to reach these subnets that are not in the IP routing table. So here's my question to you. What table are they talking about here if it's not the IP routing table? And what command would I type to view this other strange EIGRP table. That's right. Jonathan and Abu Bakr, you guys have got it correct. And Jonathan, yes, we want to do the show IP EIGRP topology command to view the EIGRP topology table. Okay, so let's see here. Let's go ahead and take a look at that. Show IP EIGRP topology. And we're trying to look at this specifically from the viewpoint of, is there a third path that's not in the routing table? And it looks like there is for most of these. So we can see here, just for example, let's pick one at random. This one right here, we can see the first two paths, that's what we saw in the routing table. And then there's this path that's not in the routing table. And we see that over and over and over again. Here's another one. Here's another one. Okay, so there is a third path that EIGRP knows about, but it's choosing not to install that into the IP routing table. Why? Why is it not taking that third path so we have three options to get to any of these networks? It's because in each one of these entries, this number is greater than the first two numbers. The first two numbers are always the same, like here, they're the same, and then the third number is bigger. Here, they're the same, but the third number is bigger. What do we call this number? In EIGRP terminology, what's that called? That is called the EIGRP distance. That's the technical term of the metric that EIGRP uses, the distance value. The distance value. And remember that the term feasible distance technically refers to the best distance. So if I take, for example, look at this right here, notice it says feasible distance is 20,514,000. So both of these are telling us what the feasible distance is. I would not call this feasible distance because that is not the best path. That's just a generic distance value. And what's this second number right here? That's what we call the advertised distance. So for example, when this particular EIGRP neighbor said, hey, let me tell you about this route, I can get there. When he sent us an EIGRP update about that route, he included in that update things like bandwidth, delay, reliability, and load, all the stuff that he used to come up with his own distance. So he didn't actually send us this number. He sent us all the components of the formula that he used to come up with this number. So our neighbor 9.61, if we actually got on him right now, he would show that his distance to reach this, his number on the left here, his feasible distance, would be 2,172,000. And when he sent his EIGRP update to us, he gave us his bandwidth, delay, reliability, and load that he used to come up with that. And then we just used those exact same numbers, we used the exact same formula that he did, and we were able to compute what his advertised distance is. Look at this here. Look at this big gap. These two neighbors, 9.33 and 9.57, they're actually pretty close to that network. Their advertised distance is only 28,000. And yet look at what the total distance is, the feasible distance. What a huge jump from 28,000 to 20 million. Why do you think there's such a big gap between those two numbers? The reason for that is because this router that I'm on right now, router 1, his connection, his PPP connection to reach router 4 and his frame relay connection to reach router 4 are really, really slow. You know, the bandwidth on those links is just horrible. They're really slow speed connections. So when he factored in his own distance to reach his neighbor, he says, okay, my neighbor is super quick, super fast to that network, but it takes me a long time to get to that neighbor because the link between us is really bad. And so that's why it really bumped up this distance value by an awful lot, because our link between the two of us is really slow. If we had like a 10 gig link or something between the two of us, these two numbers would be almost the same. They wouldn't be hardly different at all. Okay. So we've done objective 7 now. Okay, use a special iOS command such that router 1 adds all of these non-optimal paths into the routing table. So what we're being told is, look, right now if I do show IP route, and let's just pick one of these. Right now my routing table says it has 2 paths to get to the 9.48 network, 2 paths. And yet clearly it has a 3rd path here. So we're being asked, let's type in a command somewhere so that that 3rd path actually gets installed into the routing table. So I want you to tell me, what is the full command and any keywords that would go with that command to make this work? So Jonathan's got the command. It is the variance command, but variance requires that you put a number after it, a multiplier. What multiplier do we need to supply so that all these routes that have a 3rd option, that 3rd option gets placed into the routing table? That's a little tricky. That requires, unfortunately, a little math to figure out. And a little bit of artistic creativity. So let's go ahead and get rid of all that. We don't need this stuff anymore. So here's basically the way you would do this. I'm just going to pick a route at random. Let's just stick with the one we were doing, 9.48. And here's the way you try to figure out, or at least a starting point to figure out your variance multiplier. So what you do is you take your feasible distance. Actually, no, you take your worst distance, in other words, route that is not in table, which would be my 3rd entry, and you divide it by the feasible distance, and then round up to a whole number. So let's just do it with this one. Our worst distance in this particular case is this number right here for that particular route. And we're going to divide that by the best distance, which is the feasible distance, right there. And if I do that in my calculator, because there's no way I'm going to do that in my head. Actually, you know what? I probably don't have to do it in my calculator. This is 21 million and something. This is 20 million and something. So that's going to be like 1 point something. So it's going to be 1 point something. And then when I round up, after rounding up, it will be 2. So if I do variance of 2, it will definitely, at least for this route, it will now take this one here and install it in the routing table. What I don't know is, will that work for some of these other ones? Because some of these other ones might be greater than 2 apart. So that's why I say it's kind of an art form here. So let's just start with a variance of 2 and see where we go. Router EIGRP 100, variance 2. Okay, so let's see if that worked for the majority of them or if we get lucky for all of them. Looks like it worked. Everything I can see here now has 3 entries. Well, here's a couple that didn't. Right here. These 2 do not have 3 entries. 8.128, where's that? Okay, well that's on router 3, 8.192. So it looks like the loopbacks on router 3 still only have 2 paths. But that might be all that they do have. Let's take a look. Let's just focus on 8.128. Show IP EIGRP topology. And let's look in here for 8.128. Where are you? Here it is. Yeah, see that one? It only has 2 paths anyway. So there wasn't even a 3rd path that was available for it. And the other one, 8.192, is probably the same way. Haven't gotten to that one yet. Yeah, 8.192, which is loopback 1 On router 3 also, only 2 paths. So that worked. Variance of 2 covered every single subnet that we needed to cover. Now, however, that only covered our IPv4 routes. What about our IPv6 routes? Show IPv6 route EIGRP. See, we're right back to the same thing here. Show IPv6 EIGRP topology. So can't forget about our good friend IPv6, you know, the red-headed stepchild. We want to make sure that he doesn't feel left out in the cold here. So let's go ahead and do our variance command for IPv6 as well. IPv6 router EIGRP 100 variance 2. Show IPv6 route EIGRP. And there we go. Now IPv6 is happy. Now, Frank asked a very good question. He says, why would you want the non-optimal paths in the routing table? A couple of reasons. Well, for example, let's go back to our topology diagram. Previously, the way it was that on router 1, to reach all of these subnets over here, he was choosing 2 paths. He was either going this way or he was going this way. So, you know, imagine for a moment if this router, let's imagine that this was actually a really physically distinct interface. We know actually it's on the same interface, it's just a sub-interface, but just humor me for a moment and pretend that this was a totally different interface, like, you know, serial 1/2 or something, and that one was not installed in the routing table. So now imagine that there were hundreds or thousands of employees down here, and they were all trying to get to some popular network, let's say network A as an example. Well, with all their traffic coming into router 1, before I did variance, he only had 2 interfaces to choose from to send those packets out. So even though there was a third potential path, yes, it's true, it wasn't the best path, but it was an available path. He couldn't use it. So if we have tons and tons of packets coming into router 1 going to network A, there's a possibility that we might overload these 2 interfaces. Maybe these 2 interfaces get so overwhelmed with trying to transmit out all the packets that their memory buffers, their queues, get consumed. There's no more memory left to transmit, and so we just start dropping packets. So rather than dropping a packet, it's probably a better idea to open up that third route, even though it's not as good, so that we have a third alternative interface to forward those packets out of. That's one popular reason for doing it, so that you don't overwhelm 1 or 2 egress interfaces. And that's probably the best one I can think of at the moment. Okay, so that completes task number 8. Task number 9. Modify the EIGRP neighborships between router 2 and switch 3.